Okay. All right, quick overview. Vectors, we got dot product, we got cross product, and projections. One of the main applications of dot product, the projection of V onto W, is V cosine theta. Okay, the magnitude of V times the cosine of theta. So right here is the projection. Kind of label that small, but I think we understand that's the projection. And it's just magnitude of V times the cosine of theta, just the adjacent side of this right triangle. So the vector projection, we multiply the scalar projection by a unit vector in the direction of W. So here it is, just V cosine theta times W over magnitude of W. In terms of the cross product, V dot W is magnitude of V, magnitude of W, cosine of theta. So we can see that we get magnitude of V cosine theta if we just divide the dot product by the magnitude of W. And the vector projection is just this. Scalar projection multiplied by the unit vector again. Now you see a formula that obscures the trigonometric relationship where the text will put W, magnitude of W squared in the denominator, which is correct, but not very connected to what's really going on with the projection. So I prefer to write it this way. Otherwise, you tend to just follow a thing as a formula that you don't really think about, which doesn't reinforce anything and leads to a real potential for misapplication and doesn't reinforce, again, what you need to really understand. Okay, so we have that, okay? Now, not doing this particularly in order, when you have a path in space, now there's a K component, but for the sake of space, I'm not going to write out a K component, but if you have a path in space, you'd also have a K component, Z of T times K. Again, for space, I'm going to suppress the T notation and just say this is, okay, I'm going to put a Z prime, or Z of TK on here. You're going to have an X prime I plus Y prime J plus Z prime K. This is in the direction of motion. T equal R prime over magnitude of R is your unit tangent vector. T prime is normal, and we need to understand why T prime is normal. It's normal because of isosceles triangles, and you might want to review that. I don't have time or space to prove that the rate of change of a unit vector is perpendicular to itself, but it comes down to isosceles triangles. Very easy to prove, just using 8th grade geometry. Okay, T prime is normal. And then just refer to an isosceles triangle. It's not a delta, it's a triangle symbol, but of course it looks the same as a delta. N, which is T prime, or the magnitude of T prime, is your unit normal. R double prime if T is regarded as time, R double prime would be your acceleration. Whether T is regarded as time or some other parameter doesn't really matter. If you think of it as acceleration, you might use different terminology in referring to it, but it comes out the same, and the result is the projection onto the unit tangent vector of R double prime is the tangential component of R double prime, the component parallel to motion, or parallel to the direction of the curve. And R double prime minus the projection onto T of R double prime is the normal component of R double prime. Then we can draw that. You've got a curve at any given point. You can have a unit tangent vector. Well, you can have R prime. You divide R prime by its magnitude. You have your unit tangent vector. And then you have R double prime. Just looking at where I'm going to label things. Okay, we have R double prime here. Going to make it a little longer. So. You project R double prime onto the unit tangent vector, or onto R prime, for all that matters. And you get pretty small picture here, but we've drawn the picture before, so use it for reference. You get what I'll label as R double prime parallel, the component of R double prime parallel to the curve at this point. And if you subtract this from this, now you subtract the parallel component from the R double prime, well then here's negative R double prime parallel. You end up with R double prime perpendicular. That's an important picture, important idea. And you have a lot of the dynamics of motion along space curves right here. You know the physics of the situation. This is centripetal. Here's your centripetal acceleration at the point, and here's your acceleration that speeds you up and slows you down. Centripetal acceleration is perpendicular to your motion, so it has no effect on your speed. The R double prime parallel is in the direction of motion. That has an effect on your speed. So in this case, we'd be speeding up, and of course we're on a curve, so there's the centripetal acceleration. There's also an osculating curve. So I'll just kind of put in parentheses. I'm not going to osculating curves in the plane perpendicular to R prime and R double prime. And since I mentioned that, I guess I better mention the binormal vector. I don't want to do that. That's something clean. You could get rid of that without smudging it. Okay, B equal cross product of your unit normal and unit tangent vector is your binormal. Your plane, the motion is perpendicular to your binormal. And here I said the plane perpendicular to R prime and R double prime. I should have said the plane parallel to R prime and R double prime. In other words, the plane in which you're temporarily moving. The binormal, so you're moving along this curve somewhere in space, and you're moving in this direction. Your normal is in this direction. Okay? Then your binormal is the cross product here, perpendicular to both of them. So that's a very important picture. To get your osculating curve, you use v squared over r. To get the radius of your osculating circle, that's the osculating curve. Osculating circle, I don't know what's the matter with my. So the radius of your osculating circle is v squared over, well, the r, such that v squared over r equals your centripetal acceleration, this component of r double prime. Again, don't have time to detail this. Now, I mentioned plane, okay? So I wanted to do this so I could talk about the plane right here, okay? Plane through x naught, y naught, so z naught perpendicular to the normal vector m. Okay. Point x, y, z is on the plane if and only if this vector, which goes from x naught, y naught, z naught, which is in the plane, to x, y, z, has to be perpendicular to your normal vector. So there's your equation of a straight line, or of a plane. I'll do this in terms of a tangent vector, although that's not always the case. Okay, parallel, line through x naught, y naught, z naught, parallel to any vector. But since I'm talking about a unit tangent vector from here, we'll say parallel to the unit tangent vector. I'm not going to do terms of dot product. Could. But that would be more complicated than necessary. And I could have started it the same way anyhow. I'm getting into a little notational difficulty here. I could do it, I could use a small t for my parameter, but I've got a big T here. So I'm not going to use the big T, although I could call this vector anything I want to and put it into this context. We'll just say parallel to some vector v. There's your line. through a given point parallel to vector V. Now you can go back to the pictures I've drawn. Don't really have room for the pictures. Or the pictures, I believe, that are in your text, and see this represented graphically. Okay, well, this is a bunch of really important stuff about vectors, lines, planes, and so forth. Okay? And it goes into the space curve idea. And here's most of what you need to know about a space curve. Now, one thing I don't like about using this camera as opposed to zoom is I can't pause it. So it's going to get broken up into a bunch of videos, but let's go ahead and pause for a second.